Now let's take a look at our integral formula for the natural logarithmic function. And if you recall, when we were talking about our basic antiderivative rules before, we had our power rule restricted to the case where n was not equal to -1. This was because if we have x to the negative first power, then we end up with 1 over x, and trying to apply the power rule there would result in a factor of 0 in the denominator. Our natural logarithmic integration formula fills in that blank. Since the derivative of ln x is 1 over x, then we have the antiderivative, or indefinite integral, of 1 over x should be natural log x. Natural log absolute value of x to take care of the fact that we can't have negatives inside of the natural logarithm. And then plus that constant c. So let's look at a few examples of integrating using this formula. First of all, as always, constants can be pulled out of integrals. So if I don't have 1 over x, but I instead have 2 over x, I can just pull that 2 out. And that leaves me with the integral of 1 over x dx. So this would be 2 times 1 over x integrates as natural log absolute value x plus c. Now, remember our integration formulas are fairly rigid, and by that I mean if I have something like 1 over 4x minus 1, I can't just directly apply that logarithmic integration formula and just pretend this was the same thing as 1 over x. Instead, we have to use a u substitution. We're going to set u to be that denominator of 4x minus 1, and that means du then is 4 dx, and so dx is du over 4. This allows us to then rewrite the integral as 1 over u. Dx was du over 4, so I'm going to write that as du, and I'm going to pull the 1/4 out in front of the integral. And so I have 1/4 natural log absolute value u plus c. The absolute value of u, we then need to substitute back in that u is 4x minus 1 plus c. And that's it there. Now, the approach of just setting the denominator to be u and making this work as a logarithmic integral isn't always going to be the easiest way to go about things. In this case, if I let u be x plus 1 squared, the entire denominator, the derivative of that would require a chain rule and wouldn't actually cancel out the 2x in the numerator. For this particular example, instead, let's try u just being x plus 1. And the reason why this is going to be a little bit better and actually work out is picking a linear u like this allows you to rewrite x in terms of u easily, and then if there are other factors of x that need to be replaced with u's, you have something to do that with. I'll show you what I mean. In this case, we have du is equal to dx, and our substitution so far then yields 2x over u squared du. Now, we still have the problem of there being a u in our integrand, but we can rewrite that substitution equation as x is equal to u minus 1. This then gives us, I'm also going to pull the 2 out of the integral here, so we have u minus 1 over u squared du. Now everything's in terms of u. If we'd set u to be equal to x plus 1 squared, then we would have to square root both sides, and that would get much messier. But picking a linear u, like x plus 1, allows us to easily rewrite it in terms of x. So let's separate this into 2 separate integrals. We have the integral of u over u squared, that's 1 over u, minus the integral of just 1 over u squared du. Okay. So I pulled the 2 out of everything. We've separated this into 2 separate integrals. Sorry, our du should be inside the parentheses there. So we rewrote this as 2 separate integrals, 2 separate terms, and now we can integrate each one. Okay. The first one, that is our natural logarithmic property. So this is going to be the natural log of u. The second one, keep in mind that u to the negative second, or I'm sorry, 1 over u squared is u to the negative second. So let me just note this is the same thing as u to the negative second, and that's going to integrate then as u to the negative first over negative 1. So we would be subtracting negative 1 over u. And then we'll just tack the plus c on to the whole thing. Okay, so I did do a little bit of rewriting from here. This u to the negative first, that's why the u's in the denominator, and then the negative from the negative 1 in the denominator, I just pulled out in front. Okay, So let's talk about simplifying this. So I've got 2 times the natural log of absolute value of u. We need to replace the u with x plus 1. And then we're minus a negative, so this is going to become addition. I'll distribute the 2 into this term as well, and then the u in the denominator will rewrite as x plus 1, and then we're adding the c to everything. Okay. Now, one more little trick that we may have to use. In this case, if you took a look at this integral, try letting u be the denominator, you're not going to get the numerator to cancel out. If you try letting u be the numerator, you're not going to get the denominator to cancel out. Instead, what we're going to do is actually perform the division of x squared plus 1 into x squared plus x plus 1. So this is that long division process. This doesn't divide evenly, but we're going to end up with a quotient and some remainder. So recall the way this process works. We're going to divide the lead terms. X squared goes into x squared once. Multiply back. 1 times x squared plus 1. We subtract that from what came above it. The x squareds are going to cancel. The 1s are going to cancel, and that's going to leave us with just an x. So that's our remainder. So we have our quotient of 1 plus the remainder of x over x squared plus 1. So that's how I can rewrite the integrand. We have the integral of 1 plus x over x squared plus 1 dx. So now this separates us 2 separate integrals. The integral of 1 dx, that part's easy. For the second part, let's do a u substitution and let u be the denominator of x squared plus 1. Du then is 2x dx. So dx is du over 2x. So we've got x over u times du over 2x. So one more step to rewrite that second integral. We'll pull out the 1/2. The x's are going to cancel, and we'd be left with 1 over u du. Okay, so the integral of x dx, that's just x plus 1/2 times natural log absolute value of u plus c. Lastly, we just have to substitute in that u is x squared plus 1. So we have x plus 1/2 natural log x squared plus 1 plus c. And notice we can drop the absolute value bars there since the quantity x squared plus 1 is always positive.